Hello, everybody. Welcome to Question Time at Padakshep. Padakshep is a non-profit organization aiming at the betterment of underprivileged students from West Bengal, India. To know more about Padakshep, please visit our website www.padakshep.org. Question Time at Padakshep is a series of online events broadcast via Google Hangout on air, where we interact with the eminent people of our society in order to know more from them. To see our past events, please visit our blog, blog.padakshep.org. Today, it's a great pleasure to have Professor Rajesh Gopakumar with us. Professor Rajesh Gopakumar is a theoretical physicist at Harish Chandra Research Institute, Allahabad. He obtained his integrated MSc degree in physics from Indian Institute of Technology, Kanpur in 1992. He received his PhD from Princeton University under the supervision of David Gross in 1997. After a few years as a research associate at Harvard University, he joined HRI in 2001. He was also a visiting fellow at Institute for Advanced Study, Princeton from 2001 to 2004. Professor Gopakumar was awarded the prestigious ICTP Prize in 2006, Swantishwaru Bhatnagar Prize in 2009. Presently, he is a member of Indian National Academy and Indian Academy of Sciences. Welcome, Professor Gopakumar.
Thank you. It's a pleasure.
So first, let me introduce our other participants. So myself is Arnab. I am doing my PhD at University of Cambridge. And we also have other volunteers from Padakshep. So we have Masood. Masood, please.
Welcome, Professor Gopakumar. This is Masood. I'm doing PhD at Harish Chandra Research Institute, Allahabad.
And also we have Sudipto, he's also at HRI. Sudipto?
Welcome, Professor Gopakumar. I am Sudipto Singharai and I am doing my PhD in physics in HRI, Allahabad.
So, so we have divided this session into several parts, and in the first part, we would like to ask some questions about you and your academic career. The first question is that you stood first in IIT JEE exam in 1987. This is obviously a big achievement. As a young student, what was your feeling at that time?
I mean, yeah, it's of course the society in general sees the IIT exam as a very big thing, and it's made out to be a big achievement. But yes, it is an exam like many other exams, and it is of course a tough exam. They make things difficult because so many people appear for it. But I think there's some element of luck and everything also in these things to come first. I mean, at that time, of course, I was a student in class 12. Of course, it felt good to this thing. I had not, of course, one doesn't expect something like that because, as I said, it has an element of luck in that. Somehow the IIT exam was not so important for me because I was not planning to do engineering anyway. But people had told me that IIT Kanpur had a good MSc integrated program, and since many of the BSc programs in Kolkata in physics were facing problems in the exams not being conducted in time and so on, since I heard well about the teachers in IIT Kanpur, I thought I would, that's why I gave the exam to try to gain admission to that program. So the exam as such was not so important. It was mainly hoping to have that opportunity to go to IIT Kanpur. So yeah, but of course, in some way, it sort of that thing about the IIT always stays on people's. It catches people's imagination that okay, someone is doing physics after getting into IIT So many people were very shocked. Many people tried to advise me why I'm doing such a thing, and so on. But anyway, yeah. But now it is more than 25 years ago, and
so long before the exam, you have already decided to take physics as your subject. So when you decided to take physics as your subject, and what was your motivation for that?
Probably in a very clear way. I probably started really thinking about taking physics for my college. This thing maybe sometime in class 10, maybe class 9, 10, and more probably in class 10, if I remember. Though I had been interested in mathematics and physics before itself, and and like to read read more about these topics, and I was fascinated by it. But at some point, I felt that the conventional sort of options that people followed was not to my liking, and I would prefer to try to spend my life thinking about physics and mathematics. So that was a decision. Yeah, it certainly was before my class 10 exam. I know for that for sure.
So was there any particular incident or book or teacher or something that stimulated you to take physics, or it's just continuously it was in your mind?
Yeah, I think it sort of continuously evolved in the sense that I was interested in mathematics and chemistry also at that age. I used to try to do before class 6, 7, 8 and all. I used to try to have some make some small chemical reactions at home and so on. And it was interesting to understand. Then from chemistry, I learned about atoms, and then about the Bohr model, and from there the notion of quantum mechanics and so on. And also parallelly in mathematics, also many new things. There were some classmates who were also very interested in mathematics, and so we learned about things which were not in the school syllabus, about solving cubic equations, about doing non-Euclidean geometry. So these things were very fascinating, and there were some science magazines whose articles were very interesting at that time. Unfortunately, nowadays there are no good science magazines for children in India, but there was something called Science Today at that time, which was not so bad, and it had some good columns by good scientists.
So then you took physics as your undergraduate and for your graduate and undergraduate. But when you decided to take string theory for your area of research, because most of your work is on string theory and related areas. So when you decided to take string theory for your PhD or your particular...
well, actually, technically speaking, many people may not realize, but my PhD was not in string theory. My thesis topic has, my thesis itself doesn't really use any string theory, or it was more something in quantum field theory and mathematical physics. For a while, actually, I was resistant to the idea of studying string theory.
Any particular reason for that?
Sorry?
Any particular reason?
I was not particularly convinced that it was very, I was not very much convinced by all the reasons that people gave for why one should study it. And the only reason I felt, and in a way, it still is sort of one of my main reasons, is that so this was much before any of all these duality studies, but just the old ideas that string theory might be able to describe the strong interaction in QCD. This was, and in particular, the realization in the by Toft of the large N expansion as a potential way of connecting string theory with in the QCD, the theory of the strong interactions. That seemed like a concrete way to try to that seemed like a concrete connection of string theory to actual physics, and that's why my PhD was more on this large N expansion and quantitative theory, with the idea of trying to make some connection with the string theory. So, of course, I studied string theory in my PhD days and so on, but with a sort of semi-skeptical view. I mean, I was not convinced, and even now I'm not 100% convinced that it is the theory that would describe the particle physics beyond the standard model. It may describe many other things, but it is logically conceivable that it may not describe particle physics immediately beyond the standard model. But anyway, but during my PhD, I had this sort of mixed attitude, though many things in my own research and the research of the field has convinced me much more about the compelling nature of string theory, and so in that sense, I have evolved my opinions, but you
are still not 100% string theorist.
Well, I mean, a scientist's job is to be skeptical, so one has to be, one should not be a otherwise there is no difference between a person who believes something on faith and someone who is skeptical. So you have to be skeptical and to weigh the strong points as well as the weak points, and realize where you might be fooling yourself, where you might be misleading yourself. So I think that's a very important part of scientific progress and scientific endeavor. But I mean, so I see the strong points and I appreciate them. But, and like I said, I'm not 100% convinced that it is the theory for particle physics, but it is. There is maybe a good likelihood, but I find much more compelling the connection with gauge theories as well as quantum gravity.
Okay, so our next question is that in Padakshep, most of the volunteers are now doing PhD, or they're just finishing PhD, or they may be starting PhD. Will be very encouraged to know what is your happiest moment in your academic or research career.
Yeah, that in a way I can answer because there is certainly one moment or one sort of few days I can remember when I once worked out a particular result which I mean it's one of the results I worked out in 1998 or so, and when I realized the connection between certain gauge theory or certain quantum field theory, so-called Chern-Simons theory, and connection to the string theory. So this was the work that I did with Buffer. But there was a certain moment in that when I was doing a calculation in which rather miraculously certain things on one side were completely agreeing with the other, and these were very non-trivial expressions. And in a way, I was really compelled about string theory from that moment, because there was something here on one side I was doing which had nothing to do with string theory. It was a quantum field theory, the so-called Chern-Simons quantum field theory, and but it was matching sort of remarkably well, term by term, an infinite number of terms, matching with string theory on what looked like a completely different which has to do with so-called Calabi-Yau spaces and so on. So all these things will seem very mathematically abstract and remove Calabi-Yau spaces and so on. Suddenly it occurred to me how they are very, they arise in some intrinsic way. They are not some strange, just some strange abstract things that you can actually calculate with them, and there's a remarkable connection. So I felt in some way that I was privileged to uncover some new fact, if not about nature, at least mathematics of nature, mathematics life in nature. So so that was certainly a moment I remember.
Okay, if I'm not wrong, that is the famous Gopakumar-Bhapa duality related to that.
Yeah, that is now called that.
Okay, so sir, we now move out to our second part, where we'll ask you some question about general question about higher studies and research. And the first question is from Sudipto, who is at present. So Padakshep has an open teaching project. We are trying to build up free online notes for students all around India, and he's in charge, and he has some question for you. Sudipto?
As you already know, Padakshep is an NGO working at the education sector in West Bengal, and we have faced difficulties time and again. So we want to know what improvement do you suggest in our basic education system?
And so by basic, you mean in the school level at, say, all levels, junior school, middle school, high school?
Yeah.
Yes. For example, if I precisely say, sir, from age of 10 to age of 15 maybe, or age of 8 to age of 15, that's the key time on lifetime. So what's your opinion on that?
Yeah, no, I think people, of course there are books and there are schools and so on, but I think to really catch and light a spark in people's minds, one needs something more than the conventional school system, conventional education system, which even when it functions at its best, which in our country doesn't always function even, in many places schools are, as you know, in such poor shape. But even when schools function, they are not necessarily geared to sort of spark the imagination of young children. And I think young children need something more, and especially in far-flung places. I think just access to some good books or some, at least for me, I mean, now, of course, the world has changed and there is internet and other things. But at least when I grew up, for me, access to some particular books really made a big difference. And these were not books that were there in my school library or even easily accessible. But somehow I came across them and I found them, and so a few good books can help to expose you to many new things. At the same time, books which are written in a very creative way, in a very imaginative way, can point you to. Can really make you excited about the subject. So I feel if there are sort of local libraries for, or even a mobile libraries in many places, which have small collection, but a collection of very good books, which are really classic books, and you can find in by pulling together many people's knowledge and this thing, you can get a list of maybe 50 books or something, in at least in sciences, and similarly probably in other areas also, which if there is a service that goes around and gives people this access to these books, I think it may make a big difference. I think a single book can change a person's life. I remember this book called What is Mathematics by Courant and Robbins. It's a very beautiful book. It's written maybe for people around class 12 or so. But it exposes, it really tells you what is mathematics. It tells you why, what are the new things in mathematics, what are the, and it explains it in such a simple way that people without knowing calculus in many cases can follow many of the arguments. But even at earlier levels, there is George Gamow has some very nice books. And there's so one can come up with many. The Russian books in my childhood used to be very good. There's the Little Mathematics Library, whole collection of them, many nice books of that kind. So these are the sort of books which I think take children beyond what is there in the school. I think you need to have some additional thing over and above what is there in the school, not only for the material, but also to give them a sense of how big the world of knowledge is and how exciting it is. So that feeling of excitement from the world of knowledge, if there's some way to communicate that, that would be, I think, good.
Yeah, so
I don't know if this was along the lines of what you had in. I mean, about the education system. So about the formal education system, you can say many things about teachers and so on, but this is a bit sort of orthogonal to the formal education system, and I think there should be more avenues sort of orthogonal to the formal education system.
But I think Padakshep Open Teaching Project has very similar ideas, but this kind of mobile library is quite new. So we will get back to you for a list of books you want to be in that library, and if we can get enough funds, we will certainly try to implement in near future. And also there is a related question, is that so the recent Government of India policy of increasing PhD intake in various research institutes has made some positive impacts on higher studies and also on research. But do you think that government has created enough job opportunities for them?
Job opportunities are being created. I don't know about the numbers. I mean, certainly it is true that many new institutes like ICERS and NICERS have been, they are the most prominent ones. New IITs have also been opened. And there are, you read about various new central universities and new institutions like this also being projected. So I think there is probably a move I mean, I think the idea is in fact that because all these new institutes need people, good quality people, that's one reason I think why they are putting pressure on institutes and other places to increase the number of PhD students. So I think it is not, at least as of now, it is probably still okay. I mean, the number of positions seem to be commensurate to the number of people coming out. I don't know whether it will stay like that in the next 10 years.
Okay. So the next question is also from Shudipta.
How do you compare in terms of quality of research, teaching and other facilities of some of the second-rank universities in abroad with that in some premier institutes like TIFR, HRI in India? What is your advice for young students who want to pursue PhD? What should they prefer?
Yeah, I mean, the first part of your question, I certainly think that the facilities, many facilities are extremely comparable between our institutes here, the ones that you mentioned, and not only the second rank but first rank universities also abroad. The facilities in many senses are comparable. of course, there are advantages of the universities being embedded in general in a larger developed society where many things function smoothly. But nevertheless, within the constraints that operate, at least for theoretical studies, it is much easier. Easier to be at a similar level in Indian institutions. For experimental studies, it's a little bit more tricky. It's not for lack of equipment or money, I think, so much, but somehow the atmosphere is not, I think, comparable still, and there are not so many centers of people so if you want to do experimental physics, then in many ways I think Indian institutes cannot compare, except maybe IISc or some things in TIFR. But for theoretical areas, certainly it can. So about the second part of your question about the advice, there are pluses and minuses. I think it's true that there are some centers and some places, but typically the Indian institutes are not very broad in their scope. So even HRI or TIFR have some good people, and you get good exposure in some topics, but there are many areas of physics and mathematics and so on that you don't get to know much about. And for instance, just the level of the average colloquia that you hear in an institute in India versus in places abroad, I think there is a difference in the level of the colloquium. And these things like colloquia are very important so as to give you an all-rounded picture of physics and the overall idea of the subject and new developments in the subject. So that is one handicap that you would face. So it's difficult to advise students as a matter of a general policy. I would say it depends case by case. If you're focused on one's area and you think you will do well in it and you're sort of confident of working on that area, then maybe it makes sense to work in the Indian institutes in those areas. There are also other advantages that you don't have to adjust to a different environment culturally and so on, and that depends on the temperament of the people. Some people are able to adjust more easily. Other people, they find it. It can be quite stressful to adjust to a new environment, new cultural and social environment, and it's not. So it depends on if you're an extroverted person, it might be easier. But if you're a more introverted person, and I know many people who have had serious problems in adjusting to life in different countries, so there are pluses and minuses, I think. So it depends from the person to person, but certainly I think if you do well from a good PhD from any of these institutes that you mentioned, you certainly will have a good standing later in your life. And I think certainly at HRI, the kind of courses in theoretical physics that you get exposed to give you a very sound grounding of your basics in physics. So and I suspect this is true for a couple of the institutes in India. So at least you will have a good training, broad base, and you have an opportunity to do a good PhD. So it's certainly not. And many students have gone on to do well. So it's certainly not a disadvantage to stay in India and do your PhD.
So, sir, often people a priori have hardly any idea about what they are going to do in a particular research field, and sometimes they used to get committed to particular direction. So, what is your thought on that? Do you suggest them to remain open in this regard?
Yes, I think they should be. I mean, my personal feeling is also that one should be very open-minded. I think a scientist's first responsibility is to be open-minded. I mean, I think that is what marks out the endeavor of science from many other endeavors, that you are open-minded, you see different points of view, you can sort of integrate new things. So that philosophical point of view, apart even from a practical point of view, I think it makes sense to be open-minded, because you may not be able to appreciate until you get into research what it really involves to do research in a particular area, and whether you may not be able to judge very well whether your strengths are being utilized in that area. There are different areas of physics require different kinds of strengths, and you need in some areas like string theory, you certainly need strong mathematical grounding and some strong mathematical intuition as well, together with a lot of physics. But in some other areas, mathematics is important, but a good physical insight and the ability to make sort of a leap of imagination, or a leap of even if you may not be able to rigorously prove something, you sort of guess or have a hunch of what is the most important factor, which enables you to throw out some irrelevant features of the problem and focus on a crucial part. That talent often helps in making progress in some other areas of physics. So different people have different strengths, and to sort of match your strengths with the topic that you're doing research in, that requires a little bit of self-awareness and also awareness of the subject, so that you can be sort of collinear. You can sort of match the two. For this you have to be open-minded. If you sort of say from class 10 that, oh, I'm going to do only string theory, then that is not the best attitude, I think.
You just mentioned that role of mathematics in string theory and in general in physics. So we have seen that mathematics has played very important role in formulating the laws and sometimes extracting the experimental results we get from the particular physical laws. So in particular, string theory has many mathematical beauties. So how much important is mathematics in studying physics, and in particular studying string theory? And what is your suggestion for undergraduate physics students regarding their mathematical abilities?
Yeah, so mathematics in almost any area of physics, I mean, including experimental physics, you need to have a certain basic mathematical training, which is why most MSc courses and so on have at least 2 semesters of mathematical methods. So there is a certain basic level of mathematical expertise that you need to have. because, as you said, the equations of physics is formulated in the language of mathematics to make it a quantitative science. And modern physics, starting from quantum mechanics, requires fairly sophisticated mathematics. And since most of the advances in physics are in some way or the other related to quantum mechanics, I would say 90% of physics uses quantum mechanics, modern physics research. You have to be comfortable with that. So in a BSc or any undergraduate training, that's certainly an important component. But it should not be emphasized at the expense of physics itself. So you should. There are some people. Who, in some ways, are mathematical, but if your interest is more in the mathematics of it rather than the physics, then in a way, I think it is better to pursue mathematics. Because even in string theory, which is probably more mathematical than most disciplines, I think the most important research and so on comes from using mathematics to make progress towards understanding some important physical questions. So if you lose sight of the physics motivation, then very soon your research will not shed light on the physics. It might lead to interesting mathematics, So one has to be careful about that. But many people also feel, oh, there's so much mathematics, so unless I learn all this mathematics, I'll never be able to do physics, or I'll never be able to do string theory. That is also not true. You learn many things as you go along. You learn calculus, and then you were able to solve Newton's equations and do things. Then you learned maybe more about matrices and operators and so on, and were able to learn quantum mechanics. So as you learn more advanced topics, you also, together with it, can learn the mathematics that goes with it, or in most courses in general relativity start with the necessary material in differential geometry. So you can pick up enough of the language along the way, and physicists tend to have a very mercenary attitude to mathematics. They just are basically looking for the results that they can apply. So you can spend a lot of time studying mathematics for the sake of it, going through all the proofs and so on, but then that will take you further from physics. So most physicists, I think, tend to, at first sight, take the results on face value, and then, if necessary, go and study the proofs, and if they need to generalize it or adapt it to some particular circumstances, then you go deeper into the subject. So people tend to go only as deep as you sort of need to. So the attitude towards mathematics is slightly different, and I think most successful physics research comes from keeping mathematics at a slight distance. Not being totally involved in it for the sake of it.
So another related question is that, in your opinion, do you think the coursework that the students go through before their PhD is sufficient? Or
you mean the coursework, the graduate coursework?
Yes.
Yeah, I think, it depends from place to place, but I think at HRI we have a lot of coursework. I think many people complain that there is too much of coursework, probably 3 semesters or so for post-MSc students. So certainly one doesn't and want it to be more than that. I think that's probably the max upper limit one should have. Though many of our students, I think, having gone through the coursework later in life, at least I've heard from a few students who have found it very useful, this coursework, and that even if they did not use it then, but later in their research and so on, they were able to, they felt good that they had done the subject thoroughly. So certainly that's an upper limit on the amount of coursework. Yeah, then when I was a graduate student, we did not have any compulsory coursework. When I did my PhD, there was no compulsory coursework for us. We just had to, on the first day you came, you were given a big fat book which had the questions for the last 10 years, for last 5 years, of all the comprehensive exam questions, and they just essentially told you, okay, the next set of exams is in January, and then there's another set of exams in May. You can appear for them whenever you want. There are some courses being offered. You want to sit for them, you're free to sit. You don't want to sit, you go home. You want to go back to India and come back in May. That's also fine. I mean, they didn't say that, but but basically it was just completely hands-off attitude, and that can work for some people, but it may not work for others also. So there are two extremes in some way. I mean, I was happy with that. I did attend some courses. There were many good courses being offered, so I did attend quite a few of them. But you could choose, and you had flexibility. Yeah. Yeah, one shouldn't also feel that the coursework will really prepare you for research, in the sense that nothing will ever completely prepare you for research. You will still have to learn new things. There will be still things you don't know, and you can't wait. One shouldn't postpone too much the research. Say until I know everything very well, so that also one should avoid.
Okay, so now we move to our third part, where we'll ask you some question on physics, and Masood has some question for you. Masood, your microphone is, I think, it's not working. Can you check?
Yeah,
it?
Is it working now?
Yes, fine.
Yeah. So, hi, Professor Gopakumar. This is a question from our beneficiaries. So they are curious to know about unification and unified theories in physics. So could you please explain for them in layman's term what actually does this unification mean?
So I guess most people have come across electricity and magnetism, and at first sight they seem like two different things. If people are familiar with magnets and they see the compass and how it's always pointing north, and how magnets are attracting or repelling each other, and there is also, you see electricity when in winter when you're taking off your sweater and so on. There is some static electricity that is often generated, or you run your hands over on cathode rays type television tube, you can feel the static electricity. These seem like very different things, so it is quite remarkable, and something that now physicists, of course, like all of you who are doing your PhD, all of you take for granted that electricity and magnetism are part of the same force. But it is clearly a very novel idea until you study it. It is only after studying in detail the forces of electricity and magnetism, in particular how going beyond the electrostatics and magnetostatics, that you realize the two are sort of related in some sense by a rotation. They are just different ways of seeing the same same force. So that idea also of unification, which comes from Maxwell, is the first is something I think anyone can appreciate. The fact that I mean, it may not be obvious, but the fact that the two are related is what is behind most of our electrical gadgets. That's how motor generates electricity from a dynamo generates electricity starting from just magnet. So clearly, unification has many important consequences. Understanding that unification leads to important consequences. So this idea, which began with these two simple forces, has people have tried to push it further, and remarkably, they seem to have succeeded. There seems to be no, as such, we don't know a reason why it had to succeed, but it seems to have succeeded in the sense that yet another seemingly different force, namely the force of radioactive decay, is also intertwined with electromagnetism in a very subtle way. So the radioactive decay of nuclei seems to once again have nothing to do with electricity or magnetism, but the discovery by Glasgow, Salam, and Weinberg of the unification of these two, the electromagnetism and the weak force, was yet another example of this. And so people have therefore gotten more optimistic that perhaps all the forces in nature, namely all these plus the strong nuclear interaction as well as gravitation, may be manifestations, but requiring it to be, so you might be able to unify all these forces into one bigger framework, and in some sense view all these forces as just different aspects of one force. So this idea has still been not conclusively proven or verified, but there are many interesting suggestions and interesting indications that this may be on the right track. So that is so there is a whole direction of research in trying to unify the strong nuclear interactions with the electroweak interactions into a larger grand unified theory, and finally unify these together with gravity into maybe something like string theory, which so these are certainly very promising ideas, and there is historical reasons why this may be a good direction to pursue, but we still haven't come to the end of this quest yet. But that's a remarkable aspect, that such a thing like unification of different forces does happen. That's one of the miracles of physics, modern physics.
Yeah, sir, I have one more question. In the language of quantum field theory, where the interaction is described by the exchange of particles, how can we intuitively understand the attractive or repulsive nature of force?
Yeah, it's I don't know of any good intuitive reason, because there are because the nature of the force. So, for instance, in electromagnetism, you have the attraction, or electromagnetism can be either attractive or repulsive. depending on the charges of the object that are interacting with each other. The nature of the interaction, quantum field theory tells you it is via the exchange of the quantum of electromagnetic interaction, namely the photon. But the photon by itself is not charged, and then the photon itself doesn't tell you that the existence of the photon itself doesn't tell you that it should be attractive or repulsive. It's more the charge of the object that governs that. So the photon just creates a long distance force, but does not tell you much about the sign of the force. So the reason why positive and negative charges exist in electromagnetism it doesn't have a simple intuitive answer as far as I can think of. I mean, it seems you can give various mathematical reasons for it. You can give you can retrace it in other ways technically, but as far as an intuitive reason, I don't know of one.
At this point, we have one question from our volunteer, Sanjay Biswas, who is at present a postdoctoral fellow at INFN. So his question is, recently in LHC, we have almost discovered Higgs-like particle, but so far no evidence of new physics has been found. So how do you see both of these results?
You mean the Higgs versus the lack of new physics?
Yes.
Yeah, the second is still not a result in the sense that it is still
a lot of it yet to be explored.
I have not found anything so far, but they have not ruled out many things also. But certainly the finding of the Higgs boson is a landmark event. It is it completes our understanding of the standard model. I mean, almost anyone would have bet that it would have been there, but since it was not found for so long, people were beginning to feel a little bit nervous. But anyway, it was very good that it's been found, and I think studying it in detail will only improve our confidence about the standard model. The lack of physics, I think it's still a bit too early. There is the LHC itself will now, after this current shutdown and upgradation, it will clearly be exploring more of this region. And given that one has found the Higgs, one can, I think, focus one's search more precisely on new physics. So I'm optimistic that they'll find something, because the standard model, given that it is working so well, one knows that within the standard model it contains the seeds of its own limitations. So its limitations of the standard model also can be seen within the framework of the standard model. So and so one should be able to, so given that the theory of the standard model is working so well, the things that that same theory tells you that the standard model can't be working too well beyond the region where you are studying it. So in that sense, independent of string theory or whatever favorite new physics model you might have, just the fact that the theory of the standard model is working very well is a good indicator that there has to be new physics, because that same theory you don't have to extrapolate that theory so much. It's basically the same line of development tells you that it cannot work so well beyond this point. So it's an interesting point to be in the sense that one can one will know very soon, one way or the other, because the standard model cannot continue working in the way it's doing. So one will be able to pinpoint how it is breaking down or has to be revised. So yeah, it's an or maybe there is some loophole that one has not theoretically thought of, by which the standard model can bypass its limitations. So yeah, so either way one will learn something, and that's the main point, I think, for science, that one will learn something now. That, so it's good time to be also there are many new exciting cosmological experiments which are suggesting hints of dark matter and so on. Recently in the space station there was an experiment that was running in the space station, and it sees this excess of positron events which might be due to dark matter, and so there are many exciting things coming from different experimental studies. Yeah, one is from so there are cosmological ones, there are astrophysical ones, there are and high energy physics experiments. So many of these things are coming together, and there will be theoretical and theoretical puzzles to solve.
Yeah, so a similar question is from one of our volunteers. His name is Arnab Rudra. He's doing chemistry in University of Utah. So he has a message. He says, "Hi, Professor Gopakumar. I am a chemist. My question will be very basic. We know the string theory are composed of strings, and I also know that those cannot be detected at this point. But what are the possible experiments that can be designed in future to observe them?"
So the strings of that people, and so string theory may be realized in nature in many different ways. So the canonical way that people talk about is in particle physics as a way of unifying gravity with the other forces, and in which case, of course, it will play a role in the understanding of quantum gravity, which in conventional way of thinking would arise only at some 10 to the 19 GeV. And that's so if the real stringy effects can be seen only at that Planck scale, then it would be very difficult to experimentally detect them or see them. But there are other ways in which string theory may enter physics. Even in particle physics, there are other possibilities that people have been considering, in which you have strings at sort of low energy scales, so these are not the sort of canonical string route by which string theory appears in particle physics, but nevertheless they cannot be ruled out right now, and especially because some of the canonical supersymmetric theories may or may not be the new physics beyond the standard model. So you cannot rule out these other options, in which case perhaps you might see signatures of stringy effects, maybe extra dimensions, and the strings in the extra dimensions are easier to observe. These could be seen even at comparatively low energies, meaning energies maybe a little higher than the LHC energies. You might be able to see these strings, but this, I must say, is only if if this non-canonical way of realizing strings in nature is what we see. There are, apart from the particle physics way of thinking about the strings, string-like excitations are present in nature in many ways. Even in a superconductor, there are flux lines which behave like strings. These are what are called macroscopic strings or effective strings. But they share many properties in common with ordinary string theories, and in some cases may be a reflection of the fundamental strings. So maybe some string-like excitations, even in the strong interactions, there is a lot of evidence of string-like excitations. People who study lattice gauge theory, who are studying the force between a quark and an antiquark and simulate that on a lattice, they find a clear string-like flux tube of the the strong interaction force, the flux of that, the electric fields or the magnetic fields, analog of electric fields or magnetic fields associated with that strong force form a flux tube, which behaves very much like a string. And our modern understanding of such gauge theories, strings in such gauge theories, is related to the fundamental strings that string theory studies. So these strings that are present in QCD, in some sense, might be realizing the fundamental strings. So these strings need not have anything to do with the particle physics. Strings which underlie all fundamental forces. That may not be the ultimate picture of the fundamental forces of the fundamental particles, but nevertheless, the string-like objects might be seen in nature and studied using the techniques of string theory. So, when someone asks how can one see strings, one can actually see them in many different areas, not just as the fundamental strings whose vibrations are capturing protons or electrons and so on. So you can potentially see these as also vindications of string theory.
So he has another question from you. He's a chemist, and he asks that chemistry is mostly dependent on movements of electrons from one atom to another, and from movement of electron from one bond to other. So will there be any way to fundamentally control strings which will enable a chemist to dictate new chemistry?
I mean, certainly not. I mean, I can't think of any immediate immediate consequence in chemistry setting for strings, at least at the level at which we have understood them. In nuclear physics, like I said, one understands, one can in some sense think of the nuclear force in a string-like language, but whether the electrons themselves are related to some string theory, and that's a question that needs to be settled. And even assuming it is difficult to see how any effect of that string-like nature in the electrons, underlying the electrons, might show up in a context like chemistry, because after all, many things they are at different energy scales, and things typically decouple or are independent at very different energy scales, just like the details of nuclear physics is not really relevant for the for the physics of fluids, understanding the physics of fluids. So it's a little bit, yeah. So I at least can't see any immediate immediate sign in chemistry.
Okay, so we have another question from Mashood.
Yeah. So is it even possible to have different physical laws in another universe? Or what I mean is that can the physical and chemical phenomena in that other universe be explained using modified physical laws?
People do talk about possible alternate universes in which some of the in which, in some sense, the physics is different, meaning there are many ways in which the physics can be different. One in which many of the constants of nature take different values. So you may have very similar laws of nature, but the constants that appear in these laws may take different values. So that you could think of, that's one way of thinking of different physics. And that is plausible that perhaps many of these constants are set by some certain initial conditions or certain many constants in nature take certain arbitrary values, and there's no reason why you could have universes in which those constants take other values. But a more radical kind of new physics would be one in which even the laws are different, meaning there might be different forces altogether, new kinds of forces, or even new phases in the forces that are realized as opposed to the phases that we see in nature here. So that's also possible. There are meta theories of physics, in a sense, or rather you can say there are theories in which you understand the properties of the physical laws in our universe as being the laws that you see at about some particular minimum in some larger potential. And if you are at a different minimum in that big potential, not only the constants, but even maybe the very forces that you see in that might be somewhat different, or at least the phase in which you realize those forces may be different. So, yeah, so certainly you can have different levels of. It's conceivable that you can have physics of a different nature in different realizations of the universe, assuming that the universe can be realized in different ways. But in cosmology, in a cosmological setting, I think many people feel that in the early universe, you could have had smaller universes constantly splitting off, in which the laws of nature took slightly different values. So there's certainly a very respectable field of cosmology called chaotic inflation, which in which you realize such possibilities. Yeah. So, but there's no evidence as of now for the existence of such a possibility, but it has been entertained.
So we have run out of questions from physics, and now we are very grateful to have you as our advisor. Would you like to say something, give some message to Padakshep volunteers and beneficiaries?
Yeah, no, well, I think it is it's certainly very great thing that you people are doing to not only have this organization which is concerned about the education of underprivileged children, but also doing many things in a new way, in a sort of innovative way. And so the fact that you're bringing new innovative thinking into this is certainly very good. And amongst the younger generation, it's very good to see people are involved with the larger questions in our society, rather than just being turned inwards into their own goals. Yeah, so I find that very inspiring that you people are involved in this, and I'm happy to help in whatever way I can. Yeah, so I feel our country has, I mean, out of 1.2 billion people, I think very few people, a small percentage, maybe 100 million people at the most, get decent opportunities to be able to pursue their strengths, or to even have their talents brought out and utilized. I mean, we are probably every day losing many Ramanujans and Chandrasekhars and so on, who would otherwise have been an asset to the world and to our country, but they are probably just languishing for lack of opportunity. And even if not singular examples like Ramanujan or Bose or whoever, but just the waste of human potential is so tragic in our society that I think if we can do a small bit towards that, that will be great.
Yeah, in time and again in future, we will ask for your advice. And my last question is that recently Professor Sen from HRI he was awarded the Fundamental Physics Prize. So whenever a physicist working in India gets such a prestigious prize, what kind of impact does it make to the concerned institute and to the community as a whole?
Of course, to the concerned institute, it was a matter of pride for all of us and great joy. And it was really exciting and thrilling to be here to get the news. And I think the whole campus, everyone was very happy, and because Ashok is such a singular person whom everyone feels so fond of and admires so much. So I think there was sort of a great deal of joy in that. And by and large, in the string community also, it was very similar in India. The string community in India also, I think everyone was very proud and very happy at this, and it certainly is good for the. It has an impact in the community of raising the morale and many things. But I was a little disappointed that the significance of his achievement was not appreciated in the country as a whole. I mean, it was very funny at that time. The Olympics were going on, and there were people. The newspapers were full of people who got some medals in the Olympics, some bronze medals and various other things. And of course, it's also a great achievement to achieve that level in the International Olympics. But I think the lack of proportion of the achievement by someone like Ashok in comparison to something, I think at the very least it is something comparable to an Olympic medal, if not much more. I mean, the society somehow recognizes those things more. The society as a large recognizes those things more, and whereas genuine things in which the country as a whole could take pride in, I think people are somehow sadly unaware of, and do not appreciate the significance.
I think news media is responsible for that, and the whole business of commercialization. I think the society will. They don't get the news because the news media.
The news media don't carry them, or even when they carry them, they carry it in such a distorted way. It was almost made out. The focus was on the money of the price. And
exactly. That's the painful thing. That Indian has got the most valuable prize of the world or something.
And also it was treated as like, almost like some lottery, a person who has won a lottery. I mean, it's not for the achievement that went into it and the scientific this thing, and that it happened in our country, that such things happen in our country, and that message people didn't pick up. I mean, people are often you see a lot of foolish pride in the media about small things that Indians do or in India has done, but when something genuinely big has been done, people are not even aware. So
I completely agree with you. So in your opinion, when can we see another Indian in the list of the fundamental physics prize laureates?
Well, I mean, I think these things are you have to be the work that kind of merits recognition at that level requires you to have deeply probe into nature's secrets, and that doesn't happen every day, so yeah. But I mean, I think overall in the country there is an atmosphere and a base, a foundation on which the future people can build on, and definitely in the next 20, 30 to 40 years, I wouldn't be surprised if there are people from India also in that bit. Yeah, so it all depends, of course, on how much value our society gives to fundamental physics, and that hopefully will continue to support its study in the society in the years to come. But but at least, yeah, a certain, I mean, a foundation is there, and there are at least a few institutes, a few people, and hopefully the number of people in institutes will increase, and over time this will lead to one needs that atmosphere to generate such work. I mean, so it's a so it's a question of preparing that ground. And Ashok's example and other things are certainly very motivating for people, and I think and that certainly helps sort of. It's a mental sort of. It gives them there's sort of a mental barrier that Ashok helps to overcome.
Yeah. Thank you very much for such an enlightening discussion. In time and again, we will ask for your advices. Thanks once again.
Thanks.
Yeah, thanks
Thank you,
for this. I was very happy to join in, and for all the nice questions that all of you asked.
Thank you.